What often happens nowadays is anytime people run an oil analysis report or do an oil analysis, be it on site or off site, what you're supposed to do is make a series of tests that will identify any machine condition, which is wear debris in the oil. You want to look at contamination in the oil, water, sand and dirt, particulates. Chemistry then as well must be checked. Is the oil the right oil? Is it got the right viscosity? Is it broken down? Is it degraded? Or is there some sort of incorrect additive package present? So all of these in any typical oil analysis report nowadays, it's not uncommon for you to have anywhere from 25 to 75 pieces of data being generated. However, even though you have all this information, when people start to do alarms, rather than alarming all of those 75 parameters, they tend to focus on very specific parameters to start with, and then make sure that they have very good alarms around those key parameters, which are indicators of problems. So, for example, in a rotating machine, such as a turbine, it would be that everything that you see here in blue would be the elements or the parameters that you would pay particular attention to first, because those are the most likely to indicate a problem before the other parameters that might be there in a common way. So rather than alarming everything, you would alarm those and focus on those initially. And that's what's quite common. So what happens? So this is not new. Most people, how oil alarms have been established and developed for the last 40 years or more, have been doing it that way. The most common approach is those elements that I just showed you back here are generally selected by the equipment maker, whoever the people are that supplied the machine to you, like very common in power generation, less so in industrial facilities. So they can give you some guidance on what the key elements that they care about and what limits that they might have. That's called goal-based alarms. Okay, they can change depending on the equipment. If you look at that image on the right-hand side, here is a whole variety of steam turbines from different organizations, and you can see here different particle count limits depending on what they are. Okay, you can also do trend change, which is rise over runtime. That is the most sensitive alarming process, but you do need to have time. Okay. Is there a question? Yes, is there a, okay, let me know if there's a question, and I'll continue. But the key takeaway here for you guys to know, okay, is that there's different ways to identify alarms. This is what's been going on for the last 40 years. So when you ask what is considered a bad sample or an incorrect sample, these approaches are what have been used in different levels of capability, okay? And this is a typical example of alarms. I'm giving you two examples here. One is a steam turbine, the other is a centrifugal compressor. I mentioned to you there's a handful of parameters that they look for. Here is an example from a refinery. And what you're looking at here is a refinery on their steam turbines where they are giving you their ISO particle count code for 4, 6, and 14. And their current and normal report is 17, 14, 11 is what they consider their alarm. Water contamination is 100 ppm. Iron is 10. Large Fe 0.1. Oxidation 20. This is what they consider their current alarms based on what their manufacturer gave them. Here is a centrifugal compressor, similar type of parameters, slightly different feedback. For instance, they care about acid number on their oil in these. That's a typical type of example of where people would start from. So they would test their oil and compare it to these absolute values. There's one big problem with this, okay? that is that a lot of people still rely on the original 40 years ago or, or 20 years changed. The condition of the facility is different. The oil that they're using has changed. There could be a change in the performance of the equipment. And what happens, they're ending up with way too many alarms. The alarms are not reasonable. And what you end up with is a situation like you see down here on the left-hand side, where if you look at that box here with sample distribution here, 85% of those samples that they were testing were in abnormal. That's crazy. You cannot manage a facility if 85% of your samples are in alarm. So something is wrong. Either the alarms are set incorrectly, or you do have a problem in this situation. The reality is that no plant manager can operate a facility today when you have an oil analysis program where the majority of your samples are in alarm. It's not possible to operate. You have to get to much more of an 80-20 Pareto approach. This is what you need to get to, where 80% of your samples are good and only 10 or 20% of them have problems. Using OEM limits or some limits that are real world, then it's not effective. Once you start your program, you have to get yourself to a point and set the alarms so that you are in a Pareto approach where 80% of your samples are manageable and the 20% need to work. And you have to do that because you have to prioritize your resources. You only want to take action on the worst samples out there. And so if the plant manager comes to you and says, hey, situation, which one do we do first? You have to prioritize. And 15 if everything else is exceeding that. So in this situation, what they have to do is start rechanging their alarms, bring the alarm up so that and there is a strategy that we want you to be aware of that most people are moving towards. So when you have a lot of data and everything is an alarm, the question you're asking yourself is, how do I prioritize what needs to be done first? And there's a straightforward way to do this, okay? And what the method of approach out there is an ASTM method, which describes a statistical analysis approach, which is called the cumulative distribution function. And what that approach does is that it works for any data set, okay, where you have a skewed or abnormal data set situation, which is common for oil analysis programs, okay? And so what you're doing is you're basically putting all the data into you're setting up all your data, and what you're saying is, hey, I only want to know the top 3%. Everything is an alarm. I only want to know the worst 3%. Give me the top 3% of samples first. I'm only going to work on those. And everything else, I'll deal with it once I solve my top 3%. So what we're saying to you nowadays is that with an oil analysis program, which is out of control, once you have a significant data set, at least 80 samples, okay, then go ahead and run a statistical set and start identifying your top 3%. It's important, however, that this works if you have equipment grouping. So the equipment, when you do your data set, make sure it's all of the same type of equipment, operating under the same conditions. It doesn't matter. It could be trucks, it could be gearboxes, it could be turbines, it could be pumps, could be motors. Doesn't matter, but keep things consistent. So what you want to do is essentially don't mix populations. Otherwise, you end up with false positives and negatives. Consistent amount of information, similar assets, similar measurement methods, similar limitations. Okay. And now what the system will do these days is that it'll take your abnormal and it'll give you new caution and alarm values that are more statistically effective. So in this particular situation that I just shared with you a few minutes ago, whereas the customer had 17, 14, 11 for their ISO code, which was the OEM guide, in reality, with their data set, their new value should be 28, 27, 21. Now, those of you in the audience who know steam turbines will look at this and go, "You're crazy. That's insane. That's the highest number I can imagine. This is ridiculous. Nobody would give you a turbine value at 28, 27, 21. That's insane." I don't disagree with you, but the data that you have is too, you're not, the alarm limit that you have is too low. So when the alarm limit is too low and everything is an alarm, you can't prioritize. So I'm saying to you is that, yes, you're going to have to raise your alarm limit to address the top 3 and 6% of your problems first, solve those, and then you can start improving and reducing your alarms later on. So this is a key factor that has to be continually done for programs to get them into control. Interrelated with this is what we call sampling intervals. So at the moment, if you ask me, "Hey Dan, how often should I sample my machine?" Usually what I've always said to you is I've had to rely on the people who made the machine, the OEM, or the lubricant supplier, or the consultant, or some sort of lab team will do it. And this is an example here of typical hours and calendar on this. Here's an example here of steam turbines, monthly, quarterly, say diesel engines, maybe monthly, quarterly, or 500 hours. Gearboxes maybe quarterly or semi-annually. Motors maybe monthly or quarterly. These are typical types of sampling frequencies, which has been used for a long, long time. They're not ideal, and they tend to be they're recommendations. But the reality is that most users, even when they have this scheduled, okay, in many cases, what happens is that they miss or delay the sampling interval for a variety of reasons. Maybe the guys that are doing the sampling are not in today because they took a holiday, or sometimes they're busy with other projects. Long story short, the trend analysis quality degrades when you are mixing and matching. And there are currently no commonly used industry standards to utilize what's known as the optimal oil sample interval. Okay, there is no way to do that. That term is a true term. It's defined as the fraction of time or distance between the initiation of a critical failure mode and an equipment failure mode. When you have this situation, okay, this is another complication. So we just talked a minute ago about the diagnostic alarms being not set correctly. Another problem with oil programs is that you have this frequency problem where it's not always consistent. In both of these situations, what is happening is that we are increasing the risk of the program being less effective in detecting problems when we need to do it. So these are issues that we are trying to resolve. We've always said it for years, but nobody has really pushed it hard enough, okay? You must record operating hours or distance on your machines as much as possible, okay? In the past, people would avoid doing it and rely on the sampling frequency that I mentioned a minute ago. So they'd say, okay, I don't have any hours on my gearbox, but I sample it every quarter. Okay, fine. That means you have to be very consistent on sampling it. So if you miss a month and you don't factor that in, that can affect your trend. in an ideal situation, you want to be recording the time as much as possible. It determines what's going on, time or distance, whatever you're using. If you're using a fleet, make sure you record the time on the vehicle, time on the machine. If it's a construction equipment, how many hours? If it's a turbine, what is the hour rate? Or I show you a picture here of a compressor. So if you have a large compressors in your facility, always if you ask me the question, which one do I use? Do I use loaded hours or total hours? I don't care. Loaded hours is more accurate, but total hours works as well. Just make sure that you guide the technician to make sure you're consistent about what it is that you're doing. Okay. But no, always have this, and this is becoming going to be very important going forward, because the new intelligence data, if you are recording the time on the machine when you're sampling, or the hours or the distance, if you're doing this consistently, then the new technologies can actually estimate for you the next time that you need to sample or the next time that you need to take action. So start doing this now. Starting to do every time you do your program, start tracking your time. It's really, really important. And the reason that that's important is that what's coming into the marketplace right now, and it'll be starting to be available next year, is what's called prognostics. So I mentioned to you at the beginning, diagnostics. So if you say, what's the difference between diagnostics and prognostics? Diagnostics talks about the condition and looking at the actual uh, data, or the description of what's wrong based on the data you have. Prognostics refers to forecasting. What happens with this information? How do I forecast my problems? This is what all plant managers are looking for nowadays. This is what all finance guys are looking for. They want to know when and where and how much when they're looking at reliability. And I think it's very hard for a lot of us in the maintenance and the reliability world to sometimes get our ears and eyes around what is prognostics. And the best way I can give you an example is weather forecasting. So if you ever see a storm, if you ever see weather guys, you'll see here something like they'll do a weather forecast if there's a storm. And you could see here that they'll have, based on where the storm is, they will use a computational calculation, and they'll kind of a cone around the trend line of where the storm is. That's basically known as a forecast, a cone of uncertainty is what that's known as. Well, what we're saying to you is that this technology can be used for oil analysis to determine when you need to do something. If you are taking a sample today and you have your time on the machine and you've got a trend, the data technology today that's coming out in the future will allow you to forecast accurately and give you time and date or hours or miles on the machine, so that you can then go to the plant manager and say, hey, I know when the machine is expected to have problems, and I have more data backing me up. I'm not giving you a guess. I'm not giving you a kind of a crazy estimate. I'm doing it based on the data analysis that's there. That's the big news that's coming. The data technology, the artificial intelligence that's now coming into these softwares is powerful enough to do what only weather forecasters could do years ago. Okay, that's the big thing that you're going to be investigating and starting to adapt in your facilities. And so, what this does for you is that based on the current sample condition, you would be able to determine a remaining useful life. And this gives you the anticipated time to failure, as well as managing your program cost. So, typically, RUL, or remaining useful life, at the moment in the industry has been linked to additive depletion and dilution. diagnostics for that yellow line, and then there's all these trails that looks like green. That looks like the weather forecast I showed you. But what this can do for you in terms, this is how the software works, is that based on today's information and based on a good alarm limit, as well as hours or miles or distance on the machine, it will tell you three things. It will tell you when is the machine is expected to go into a severe state. It'll tell you by time or date or whatever time that you will have, but it can also tell you when you need to change the oil if that's the target point you want. Okay. And the nice thing about this is that for those of you doing your on-site analysis with our technologies, you don't have to sample consistently at the same point every time. The system will help you in telling you when the right time is to sample if you have this capability in place. So that actually saves you a lot of time and effort. You only sample when you need to. And so that's the technology that's coming down. So what does this mean? So it's going to have an effect on your sampling effort. Okay. So a best way to kind of give you is that you've got, I mentioned to you at the top of the call, we have OEM recommendations which tend to have alarm limits which tend to be very consistent and conservative. You can also have alarm sampling, which we talked about, which is based on rise over runtime or frequency. Okay. But once you migrate into prognostic-based sampling or forecasting sampling, what you can do then is only sample when you need to sample. So you end up with an optimum zone. That's where you're getting. This is the most effective. It means that your cost of your program and the sample frequency is at the ideal point. That's ultimately where you're going. In other words, it's kind of an enhancement of the, if it isn't broke, don't fix it. If you don't need to sample it, don't sample it until you need to sample it. That's kind of one of the ways that the technology is aiming at. So it's able to do this. So let me give you an example of a real life study that we've had in this that is part of this. So in 2024, we applied this new software technology to a mine that was mining lithium in South America. And they had a series of Komatsu trucks that they were hauling, and they had a requirement where they had to change the oil out every 600 hours on on these engines. And the question came up, and the oil comes free. Okay. And so the question they asked was, can we safely extend drain intervals so that we essentially only need to change the oil when it really needs it? Okay. And so what the system did was with this out of 13 engines, 9 of them, they did not, but the oils that they were doing, they were able to save just on those 13 engines, they were able to save just on the oil cost $6,000 on those before they were able to do it. That's per engine, by the way. Okay. So they were able to, because, and that involves the time and the oil change being in the shop of changing those. Okay. And if you look over here on the right hand side, okay, the way you look at this graph is that here you have all these engines. Everything in green means that the oil condition is good. Okay. If it's in yellow or red, it means that the oil needs an oil change if it's in red. Okay. If it's black or dark gray here, that means that the oil is already well past its alarm limits. So what we ran here, okay, was a series of studies on these engines. And what you can see here is that using the 600 hours as a starting point, you could see that depending on the engine performance, many of these engines, they could go safely well past the 600 hours. But look at this. It's important to see that it's not uniform. So this Komatsu truck here looks like that it based on the way the oils were, this was well failing, maybe at around 500 hours, maybe. Here's another engine where it was failing under 480 hours, okay, before you saw an alarm. So looking at these here, if you only have resources for a couple of hours for engines, okay, the question is which engine would you overhaul first? I would probably do this one first because this one is barely able to this is not even making the 600-hour value here. This third engineer or fourth engineer, this one 334, because this clearly is not able, out of all the population of engines, this one here is way, way bad. So if I had to repair one engine or two engines, that's all my budget was. I've only got two engines I can fix this month because I have only so many available resources. Then I would focus on that guy and this guy first. And then the other ones, I would wait and extend them. And so when you have this type of detailed information, you can make really, really smart, prioritized based decisions. And as you do this, you're saving money very carefully. You're saving it safely. So you are saving your money by not having to do the work, but you're doing it in a way that's backing you up with data. So that based on the work that you're doing. And so that's the significant changes that's there. So in summary, the ability to forecast risk optimize preventive maintenance, okay, can avoid costs with unplanned downtime, okay, preparing, flagging data where contamination, it has the potential to catch problems well in advance before the oil crosses the diagnostic threshold. And if you prepare your data now, you can essentially make sure that you can take advantage of these new technologies that are coming down the line. Now, I can finally say to you, okay, you as a plant manager with this capability on site have very powerful information available. So if you are doing something on site right now and you are running your samples and you're doing this consistently, your data quality is much more powerful than sending it off-site and not putting in the proper information present in. So if you're able to track hours and miles on the machines, you're doing consistent data, you're doing consistent retesting, you're checking, you're watching your alarm limits and setting them up properly, then what you have is the ability then to really use the information and have some very intelligent decisions made, which can actually save significant amounts of money. So in the previous example I shared with you, they were able to show that in just within 6 months, by them starting to do this with a fleet of engines, between the reduction in unnecessary oil changes based on OEM alone, combined with sampling just when the right time, they were able to save about $300,000 all told, just on the first 6 months on those 13 engines and those applications. So for them, and they didn't do anything new, only just do what they were already doing. They had an on-site lab, they were testing, everybody was following it, but with this information, they were able to extract $300,000 more in value by not having to do unnecessary work that was traditionally required of them on a preventive maintenance schedule. So in summary, you can do this if you have the data. If you have this information available and you have an on-site capability and you're following through, you have the information that you can then change or improve upon whatever recommendations the OEMs were giving you, okay, or whatever you were doing before, but you can do it safely. And at the same time, while you're extending your drain intervals, extending your sampling intervals, you're also making sure you have an improved detection ability so that you are avoiding unplanned downtime, which is the goal of what we're trying to do. So that's the summary of the presentation. I hope this gave you some ideas, and I'm going to stop talking, and I'm opening the floor for any questions.